Of course. So, welcome to Martino Fortuna for this third seminar of the series. And so we are happy to listen what you have to say about asymptotic analysis of semi-discrete models for crystal plasticity. As before, I don't know anything about this one. So,
thank you.
Thank
and
you.
I forgot before, thank you for the invitation, of course. And so we're here. I've been here for just a couple of months. So I'm really new. This is my presentation. This is what I've been doing during my three-year PhD student. And it is about some variational models for material science, in particular variational models which are called known in the literature as semi-discrete models, and they are about plasticity phenomena in crystals. The setting in which this talk is going to be inserted is of the one of linear elasticity. Brief reminder of what linear elasticity is, what we're going to need of it. In this context, we are in R3, given an hyperelastic material omega in R3, and a deformation of the body V, then we can define the displacement as V minus the identity, which is a measure of how the points are displaced, as the name says, by the deformation. Of course, being a deformation, there is some stored energy, elastic energy, in the body, and in the framework of linear elasticity, this stored energy can be described as an integral of this quadratic energy density, where C is a four-dimensional tensor product, which is symmetric, which vanishes on skew matrices, and as a working hypothesis, we shall ask that the square should get in this sense on symmetric matrices. Just a quick word about the linearized setting here.
This norm, the square norm.
The square norm of it.
Which norm is it?
I would say I would call it the two norm, the
operator norm.
The operator norm. Oh. I mean, I would say they are equivalent.
Yes, of course.
I never bothered about, but yes, I would say. For the Frobenius, maybe it's better. And the column here just means the usual inner product matrices, so the entry by entry product.
And D is the statement. D, the operator.
And D is the derivative of U.
So is the Adamant product this? I didn't get the product.
This one, the column. I would just.
Adamant.
Adamant product.
Adamant, giusto?
No, it's fine.
It's fine.
Yeah, thank you.
I feel good with the notation.
No, but it's fine. No. It's
Mettiamo il punto
it's just
mettiamo
the.
il cerchietto noi, vabbè.
Sometimes all times is in place.
No, all times is for the tensor product, but Hadamard is just the empty circle.
Okay. And this linearization, of course, it's meaningful near an equilibrium, since the elastic energy in general is nonlinear. But near the identity, one can linearize that can be formally shown that in the case of small displacement, this is a good approximation.
Meglio se non hanno visto.
The picture I have in mind when I talk about elastic deformations in the context of crystals, such as metals, which can be described schematically. Was atomic structure can be schematically described by lattice in R3, for example, the cubic one, which is ideally the easiest one that one can work with. And elastic deformation, which is something reversible, as opposed to plastic deformation, which is something that cannot be undone. It's something that doesn't, if applied to a metal, doesn't really change the topology of the lattice. It just stretches the bound, the atomic bound, so it can be undone when the load is taken away. And the crystal lattice, of course, is distorted elastically, and this is why there is some elastic energy which is stored in the crystal. So, as I said, my talk is going to be about plastic deformations, and one of the major actors in plastic deformation are going to be dislocations. What are dislocations? Dislocations are a particular defect of crystal lattice, which is depicted here in the second image. They have long been understood to be an important part in plastic deformations, in that they lower the energy required for it to happen. A way in which dislocations are often presented is the following. Imagine to cut along a portion of plane through a particular symmetric plane of the lattice, and imagine to push simply the portion of lattice above the plane until you rearrange the bonds, and finally obtain something like this. Of course, the topology of the lattice changed in that there is an extra half plane of atoms here, the one here, which changes the topology. This is what is called a dislocation. In particular, in this case, this is called a natural dislocation, but I will just refer to it as a dislocation. The pile of atoms that are containing the boundary of the half plane, which is the extra half plane, is what is called the line, the dislocation line. It is more than a line because it's the boundary of the plane. Here, I guess maybe you cannot see it. So this is an actual picture of dislocation in titania. This is strontium. 5 times strontium, and you cannot see, but I mean this picture is actually very well depicted here. It's unfortunately it's not particularly HD the image, but you can clearly recognize the structure where there are the arrows. Important features of dislocations are that
so the arrows lie on the
lines.
Okay,
this is a good question. This is a 2D section, so it should be interpreted like cutting across this plane. And so this is a the dislocation line should be thought of as coming out of the screen. So this is just points. Of course, you can recognize there is some elastic distortion in the lattice caused by the presence of the extra plane. And also an important feature is that this elastic distortion decay quite fast as you go away from what is called the dislocation core. So the neighboring area around the dislocation. So basically, outside the disc region is basically you can recognize almost after the lattice. So there is not going to be that much elastic distortion. And of course, the deformation is plastic. There is no way, this is an equilibrium configuration. The bounds are reformed, and there is no way you can go back without applying the other forms. I'm taking it too much. So, an important object that is related to dislocation is the Burger spectrum, which is a measure of the elastic distortion caused by the dislocation. One way of retrieving this Burger vector is by means of the Burger circuit. So in the deform configuration, you draw a loop around the dislocation, And as you come back, this loop doesn't close because of the excess half-plane of events. So this excess is called the Borges vector. It's always a vector of the lattice, and it is a measure of the strength of the dislocation. If there were two layer of atoms, the vector would be twice as long. So in this sense, it's a measure of how the lattice is distorted. Okay, this is a painful slide. We want to insert this discrete argument, the discrete phenomenon that we just described, into the linear setting, which has a continuous nature. So we want to describe in a continuous fashion dislocations that are discrete in nature. So I'm looking at
It's
this.
better the other way around.
Hmm?
Going from continuous to discrete, I like more.
I mean, I guess the point is you have a framework that already exists, which is the linear one, which is how we actually do the computation, and also this is the main test. I mean, the only way I know of that is
Just in general.
linear. And so, okay, what's the dislocation in a continuous setting? Conceptually, not mathematically, not formally, the dislocation is a line, the line dislocation, and also described by the Borges vector. The Borges vector has an important property, which is they are conserved along the dislocation line. So if you're coming as a 2B from a dislocation line, at the point of branching, you have to sound the 2. And also there cannot be endpoint of the dislocation line inside of the object. This is because it is a boundary of an object. Being the boundary cannot just terminate in between in the object in the body. So how we formally describe dislocation as a measure. To a dislocation, which if you're not comfortable with this notation, you can always, for what it is needed in what follows, you can just think about a line with a Borges vector and a direction. But formally, in a mathematical setting, we describe the dislocation as a measure supported of gamma, which is the dislocation line, a tangent vector, which is the orientation I described above, and of course the Borges vector. This is the all times the tensor product, which is I don't know if you're familiar with the notation. It's a matrix whose entries are simply dij. And H1, if you're not familiar with the notation, also you can simply think of it as the length measure. So how does this act? Of course, if you have a dislocation which is a straight line, if you have okay, let's do an example. For example, if you have a vertical dislocation in the direction A3, with Borges vector B and tangent vector A3, of course, then we would describe it as a B times A3. H1 of R3. This is how I would call this line. And how does it act? You take a set in the body and you call it A. Move A is simply if B is constant, B times E3, the length of the times the length of P3 intersection with A. It's just a measure of how long is the dislocation inside of it.
That is the total variation. Right? That is the total variation, the mass.
No, because it's there is no. The total variation would be this. I keep the direction.
It's a matrix, right?
It's a matrix.
It's a matrix which takes a vector to the vector with the same direction as B, but the intensity of its projection along the E3.
Yes. If you do, I mean, how does it act on vectors? You take a vector, the product of this matrix by a vector is simply in the direction B, and the intensity, as you said, is E3 times B. I don't know if you can see this is how it acts. It's taking forever, I'm sorry. So, okay, formally, this is what I would call a dislocation. But if you're not comfortable with it, just think about a line with a foot. But why bother so much with this? Is because we're going to take limits. And this is for object of this type. There is a structural theory and compactness in this family is convenient and well understood. This is, I mean, this I would skip, but basically just states that the fact that Vogel's vector is conservative. And so, in the case, as I said before, in the elastic case, not the plastic, you try that case if mu is equal to 0. If mu is equal to 0, then the deformation was described by the local deformation was described by the gradient of the displacement. How would you, can we describe in this case when mu is not 0 the deformation of the dislocation induced by dislocation? We're looking for a strength field beta, which is to every point in the body links a matrix as it should be, because before it was a gradient of vector field. And the fact is that you cannot hope to look for it as a gradient of a function, because following the Burgers secret argument as before, the circulation along the dislocation line is non-zero, and so it cannot be an exact form, so it cannot be a gradient, a global gradient. But locally, it is actually a global gradient. But this is as much as we can ask. It's something that locally is aggregated, but globally is just a map with values in that field. And it is linked to the dislocation in such a way that its curl is the dislocation measure. So we would say that a deformation beta is compatible with a dislocation if the curl of beta is equal to. Everything clear? This is what a painful. This is an example, because maybe that was a little bit abstract. Given the dislocation I drew here, so in the third direction with constant movement vector B, what is a compatible field? This is a compatible field. It's basically just if you are familiar with the winding number, which is the form that tells you how many times you wind around something. This is the field that is. So the situation of this stuff is big, because if you do one loop again around the dislocation, you get exactly. I mean, the 2 pi's there for that, and you keep the beat. So the circulation around the dislocation line is okay. So there's nothing fancy. This is what happens. Also observe that it diverges beta diverges as the distance to the dislocation line, 1 over the distance to the dislocation line, and this is not the case. Every such string field beta, if mu is irregular enough, has to be this behavior. And from this we can also, with our straightforward computation, straightforward computation, see that they are not square integrable. They cannot be, because the curve is concentrated on a n-2 dimensional set. And this is going to play an important role. And also the kind of abundance that we're looking about is logarithmic. Logarithmic in the distance of the dislocation. CS here, I didn't say CS here, is simply a cylinder of length 1 and small and a whole cylinder with the step epsilon, with a small radius epsilon. So as epsilon goes to shrinks to zero, it diverges. The L2 non diverges. So as I said before, we would like to insert this analysis into the linear elastic analysis we presented before. So we would like to compute the energy of a strain field of a dislocation, so the dislocation in the same way we did before with linear elastic energy. But since we have just said that beta is not square-integrable, it is not a surprise the fact that also this energy being quadratic cannot be finite. In particular, a precise estimate was found by Continuum in 2015, and they take a dislocation with constant border vector B in the direction T, a dislocation line, a straight dislocation line. Take a beta, which is admissible with respect to this dislocation, and then they compute the elastic energy again in a hollow cylinder with small radius epsilon, and they found that, of course, as we said before, this energy diverges logarithmically in a small radius. But the important part of this estimate, which is more precise, is the fact that the pre-logarithmic factor, which is this function psi of c, has been established. This is what this is called the pre-logarithmic function, and it is in a way the density of elastic energy per unit length of the dislocation. And this inequality can actually be obtained as an inequality for optimal beta. So basically, what that what that proposition says is that taking a dislocation, which is maybe piecewise represented by a piecewise segment dislocation line with segments gamma E, gamma J, then we're saying that the elastic energy at fixed epsilon goes basically as Cg of dt if the Burgers vector is d and the direction of the segment is d times the logarithm. So we have a way of computing up to this constant, which may be taken to depend on the crystal lattice. But of course, we would like to say something more. We would like to study the asymptotic behavior of the elastic energy as epsilon goes to zero. To say, can we formally derive something more precise about the behavior of the elastic energy? Before that, maybe an example. In the case of isotropic elastic material, so when the elastic tensor C has this form, which is one of the easiest one we can think about, then in Gamma-convergence 2009, in a slightly different settings, but still meaningful, they derived that the pre-logarithmic factor, which is can be viewed as an relaxed density for the elastic energy per unit length, must take this form. So there are two things that are important. The first part is that it is quadratic, and the second part that this shows that you can interpret this as an anitropicity that is due to the fact that the crystals are not isotropic in certain directions, because we have the lattice, which might change the energy in the direction that you want to put your dislocation in to have optimal energy. So, a quick resume what we have done. Basically, what I've described so far is what is called the core-radius approach, which basically try to calculate, to compute the elastic energy density, eliminating a tubular neighborhood around the dislocation line. And the goal now is to say something about the asymptotic behavior of the rescaled elastic energy density. We said the rescaled the elastic energy diverges logarithmically. So we're asking when we rescale, what happens? Can we say something more precise formally? In order to do so, we should talk about a particular kind of convergence for functional, which is known as variational convergence also, but its name is Gamma-convergence, introduced in the 75 by Georgi. And so if the question you're looking for, if the answer to the question you have is the following. If you're asking yourself, suppose you have a family, a one parameter family of functional f epsilon in some space x, and you have a sequence of minimizers of f epsilon. Does the limit of this minimal point converge to anything? Does it minimize something, anything? And in what sense? So f epsilon should converge for having this convergence of the minimizers and of the minimizer of the f epsilon to the minimizer of this limiting energy function of f. To answer these questions, there is gamma convergence. I'm not going to give the precise definition, but basically what gamma convergence does is the following. If you assume some sort of compactness coercivity of the functionals, so if your minimizing points, sequence of minimizer doesn't escape, so if you take bounded sequence of points x epsilon, then you can actually give sense to a limit. So if your family of function is coercive in this sense, then what is true is that
so this is the definition of coercive.
There are many definitions of coercivity. One, I mean, this is the, I would say, the sequential one. Another one is that there is a uniform compact in which you can found all the x epsilon depending on C. Basically, you want some compact. If you're in a metric space, this is what you want. Looking for sequential compactness. And so, if your family of functional is coercive, then what happens is that the sequence of the minima converge to the actual minimum, and the minima exist. So f has a minimum point, and the sequence of minima converges. Also, minimum points converges to minimum points. So basically, somehow it is given some coerciveness, you have a way to switch from the approximating problem to the limiting problem. If you like better the approximating problem, because you cannot, you don't understand exactly precisely what the limiting function is, maybe you like to work with the approximating problem, and vice versa. Maybe you have some approximating problem you don't know how to compute. You go to you can compute luckily the gamma limit. You work with the gamma limit. When minima is what you're interested in. So, what time is it? I'm sorry.
It's 10 past 3.
So
Okay.
you have 15 minutes more.
Okay. So, okay, no, sorry, before this. So, given this
25.
Okay. So, we want to investigate via gamma convergence the behavior of this sort of functions. What do we do? So let's take a look at what we can expect of this energy. So we said that this energy, which I automatically just erased, is 1 epsilon that energy, sorry, is more or less C rel of the length of gamma I for some for a dislocation of piecewise straight dislocation. Okay. So one would say, okay, so in the limit, I should get just the COC. This is basically what it says. But this is not what we get because there can be some microstructure happening. So to be more precise, we are trying to we're taking the limit as sorry. Didn't say this before. We're taking the epsilon is should be considered as the characteristic length of the lattice. So when we're taking the limit as epsilon goes to 0, we're actually looking from a distance as the lattice is going to 0. So let's say we see a dislocation line from the distance, okay, and with Burger's vector, I don't know, 3b, okay. But actually, from from a scale, from a finer scale, we find that is composed of 3 dislocations that you didn't see before because we're too distant from that. And let's say that you want to compute the elastic energy using this formula. The elastic energy density is this one. So in this case, since the dislocation, assuming as Burger's vector of 3b, since the dislocation, the energy density is quadratic, is more or less it should be 3b squared. But the energy density for the final construction is lower, simply because the energy density is not subdivided here. So it might happen that it is more convenient to get on a smaller scale some microstructure. It is convenient to split the dislocation to get a better energy. Gamma convergence is a type of convergence being interested in minima that keeps track of the behavior. So in the limit, you are assured that you're gonna end up with an energy that remains that keeps track of the behavior. So you're actually getting something, an energy which is optimal. So we should expect that in the limit, the energy density that we're going to get is not CC, but some sort of relaxation. The relaxation in what sense? In the sense that it allows for microstructure. And so the precise statement is this one, which is a formalization of what I've just said. But let's pass over it again. So we're considering consider the energies we have been dealing with so far, which are these ones, and optimize, take a dislocation mu, optimize in beta. So take all the deformations that are compatible with mu and take the best one. This is basically as this sense, this infimum here, this part of the energy can be considered as the energy of the dislocation. The elastic energy of the dislocation, and it is what you end up with the here. And in the sense of gamma convergence, this energy converges not, as I said before, to something that has FCC as an energy density, but to something that has an energy density which is lower in general than FCC, which is this one. Again, this is each one is the length measure, so this simply this is a line integral over the dislocation. So the so the gamma limit, which we call is 0, is basically simply sum of this configuration, sum of the ring of C L above the which is in general lower because of microstructure. There are a lot of results in this direction in different settings with different energies, linear, non-linear, where all the dislocation lines are assumed to be on a single plane, and you can deploy different
So the
energies.
question is, are you able to find this phi rel? Or
It exists.
it exists, but you cannot find.
This is a painful. This is the drawback of.
So it is not constructive.
No, this is actually what I would like. I mean, if you have to take something away from what I would like to say today, is the fact that this is a nice way of forming deriving things,
yes.
but there are some drawbacks, and in each case I will show you the actual computing of the energy density is something that is not that simple. See,
Size C is explicit, right?
size C is actually very explicit. I mean, sorry, another second.
Okay, so it's this energy per unit length.
Yes,
issue
yes,
now.
it is. I mean, I said in one case it was computed very like 10 years ago more, and it was d squared plus.
The one you mentioned. Okay.
Okay, but I mean, this is explicit, but also in general, you can compute it with, via variationally, and it's quite explicit. I mean, it's just a minimization over a vector and one-dimensional function. So you can do it. That is not a problem. C is not a problem. The relaxation is the problem. And sorry. And okay, I didn't want to write down what is the actual formula, but let me comment since maybe it is interesting. CRL of dt is the relaxation of T. In what sense? It is the infimum of okay, I inverted the beta tilde of gamma. So it is the infimum of the unrelaxed energy. Okay, taken over what? Taken over all the all the dislocations that agree with the straight one with Burgers vector B and direction T outside, let's say, a ball. Is it more?
What is the size of the ball?
B tilde. I mean, you take a dislocation that is you fix the boundary condition outside of the ball, which is given by dislocation straight with the direction T, Burgers vector B, and then you allow inside of the ball the integral is taken in the ball, of course. Okay, and then you allow inside to do whatever you want, and you take the optimal shape. And so, in this sense, this is a relaxation because it says, okay, I take a dislocation, but maybe it is not being straight is not the best option available. Maybe you should do this. Okay, and this is not something that I don't know how to actually compute this thing. It might be interesting for sure, but I don't know.
It's complicated.
It is complicated. Also, I mean, in here. In Conte, Garoni, Massacesi, they actually try to do some computation with the easiest option you get, which is this one for the isotropic case. And also in that case, you can say basically the only thing you can say is on the vectors A1, A2.
Do you have negative results? So, I mean,
what cannot be?
Yes.
Yes, for sure, because it has to be additive, for example, and linear. Whatever, I mean, inside of this, I don't know what else to say, but you have some condition. And so another question that one may ask himself after having obtained an energy per unit length of the dislocation, a relaxed energy, is okay, but this is an energy per unit length. If I take a system dislocation with total length of dislocation at the divergence, can I say something? Can I rescale this energy in such a way to obtain something meaningful? Again, in the setting of gamma convergence. Why is this interesting? It's not something. I mean, it's not just some mathematical exercise, but in the spirit of gamma convergence is again the game we played before. I have something that I would like to make sense of, and maybe in the limit there is something more useful that I can compute fast with if I derive it with gamma convergence. For example, let's say that I have a diffuse density of dislocation. So I have a piece of metal that is heavily distorted, and the total length of the dislocation line exceeds by many order of magnitude the total scale, the usual scale of the metal, like light years. And so maybe it would be smart in practice to have not a line energy, but something which is diffused, like an average of dislocation. For example, let's say that I have this. So let's call this average, this measure of the dislocation diffused, and let's say that it's B density. Okay? So I have a diffuse dislocation with intensity B on this piece of metal. Then I look closely at a smaller scale than the macroscopic one, and then I realize that maybe I can obtain such a configuration dividing on dislocation line with a smaller Burger vector. So macroscopically I see B, but actually maybe on a mesoscale I have uniformly distributed dislocation lines with Burger's vector sigma B. So the dislocation lines are separated uniformly by the distance sigma, and consequently, I would like to have the Burger's vector that are smaller as sigma. So okay, let's try. I would like to. I try to compute the energy of this configuration with what I just obtained, which is the relaxed energy. Okay, I compute it. The only thing I can do is this one. So basically, I compute the CRL, the relaxed energy over all the lines. How many lines do I have is 1 over sigma if this has unit length. So since the unrelaxed density is linear, as we already said, the energy diverges like 1 over sigma. So if we believe that this is one of the actual possibilities, then of course we have a lot of dislocation from the space. Maybe this is an interesting energy. And so what do? The relaxed energy diverges like 1 over sigma. We simply rescale by sigma the energy and see what we get in the limit. In what sense in the limit? Again, as gamma convergence, because otherwise we would just get game as before. So it's here. And the statement we studied together with the in this problem, and this is again what I just stated, but maybe in a slightly different manner. And what we see is that again there is a relaxation phenomenon that happens, and slightly different than the first one because before we had microstructure. In this case, it's going to be a problem of convexity of the of CRL, which might not be convex, and it is a classic fact in relaxation that convex energies are optimal. And given this relaxation step, in the end, what you get is something that is plastic energy density with a plastic energy with density, which is again as before, as I just said, the relaxed energy with respect to the CCRL. But now what happened is that this is important. That the functional limiting energy is not defined on dislocation supported on lines. Now is defined on something that might be diffused. So is defined on measures that might be absolutely continuous with respect to the vector. So this is the way. So we actually obtain what we wanted, because in principle, at the beginning we wanted to give meaning to what is the energy of a diffused diffuse dislocation system. And
Sorry, Martino, but does this say that you can use G in place of C rev? Can you replace C rev with G? This is the meaning of this result.
the meaning of this result is that if you, as sigma gets smaller, so as the approximation gets more and more relevant and meaningful, then yes, the minima of one problem can be approximate the minima of the other. And so low energy configuration of this energy when sigma is small are actually well studied with this energy. So given you can compute G, you don't have to bother with all interactions because of course if you have a lot of dislocations, you have to compute all the stuff. Because you have to compute interaction energy of within dislocation. I draw them straight, but they're never going to be straight. They're going to be whatever. And so you don't bother with that. You just compute G, and this is, I mean, given the complexity, computational complexity of G, this is what you get. Of course, G, I don't know what G might be. For example, the only example I found around was in the case of C rel of B T equals to B, which I don't know if it is actually realistic, because maybe you should probably have like the one on the Manhattan norm. This is more realistic than okay. Then G of A, because G is a function defined on the matrices, is the spectral norm. Transpose. The trace. Is it right? Is this the spectral norm? Lambda.
This is the
Frobenius
norm. This is the Frobenius
Yes,
norm.
it's again the Frobenius norm. Okay.
It is the Euclidean norm of the spectrum.
Yes.
Yes, it is Frobenius.
And this is the only actual computation that I found. And it was computed in here actually, because in this paper the authors proved the two-dimensional case, which basically means supposed to have all the dislocation lines contained in one single plane. So the kinematics is more easy, because you cannot have, I mean, they're just in a plane, and you can use different tools. And we prove the three-dimensional counterpart. This problem is actually okay. This problem is actually linked to another one that I'm not gonna explain at length, because this is part of a bigger attempt to prove something in a different rescaling rather than the logarithmic one. So what we tried so far. What we studied so far is the logarithmic the logarithmic rescaling of the elastic energy. But we have seen that since each dislocation periodic length diverges logarithmically, this is useful just in the case of a bounded number of dislocations, because each dislocation contributes like log epsilon. If you divide just by log epsilon, you can just hope to obtain something meaningful for a finite number of dislocations. So what happens when you have non-finite number of dislocations? So if you're asking, okay, I have a lot of dislocation, what can I say? What are the relevant scalings? 2 minutes. Okay. Of course, we are not going to say anything about it. This question have been answered for now just in 2 dimensions, and the first work in that direction was done by Garonion and Consiglione in 2010 in the 2-dimensional case. So the 2-dimensional case can be retired from the 3-dimensional case in the setting of cylindrical symmetries. So your dislocation are straight lines with the same symmetry of a cylindrical domain. And so you can view dislocation as points sitting on the intersection between a cross-section, which is in your domain now, and the dislocation line. And in this context, then the dislocation can be seen as Dirac deltas centered on the points, sit on the points with the Borges vector, with multiplicity in discrete multiplicity. And the authors studied different regimes in which the number of dislocations can diverge. And they, in particular, one of the most interesting is the case in which the number of dislocation goes as a log epsilon, because in this case, basically, you have a balance of the self-energy of the dislocation, so the energy near the core region of the dislocation, and the interaction between all the dislocations that now is going to be important because we have a lot of dislocation. And the result that they proved is this, again, in terms of gamma convergence. The relevant value scaling right now is log epsilon squared, because you have the previous scaling for one dislocation, you have log epsilon dislocation, so you have to rescale also by log epsilon. And again, they prove a gamma convergence result in which you find morally the same energy density as obtained before from the previous statement that I showed you, plus an elastic energy that cannot be ignored in this rescaling, because we have a lot of dislocation that are going to cause an overall elastic deformation in the crystal that before could be ignored. This is hidden in the gamma convergence. In the tool gamma convergence is the choice of opportune topology in which you are taking the limit, because maybe you don't have compartments with the wrong one, maybe all the minima are trivial and you actually end up with nothing interesting. So the choice of the topology is really, really important. In this case, the topology that is meaningful is this one. It's just curiosity. But basically, what I've been trying to do in the last month is do the same, try to obtain mutatis mutandis, the same result for the 3-dimensional case. And the previous result is a step in that direction. And so what we're actually writing right now is something along these lines. Of course, all the indices are going to be changed, but the nature of the statement is not the same. So, I guess I'm done.
Oh,
thank you very much.
Thank you. Questions?
So you have 2 steps, 2 layers of relaxation in a sense. First, you get this relaxed density of energy per unit length, and then you have this complexification, complex envelope. And you say that if the first step was that one, then it would be possible to determine the second step too. Yes, in this paper of 2010. But these assumption that you have a linear behavior in the last
right.
it sounds
Yeah, they are.
strange, right? Because that should be below anything else, but you have a vertex. It's the graph is a vertex. As a vertex at the origin.
Yes.
So what does it happen if you instead consider a function which is strongly convex? Is it possible to compute G if psi L is P homogeneous with P larger than 2, for example? Do you think it is feasible to explicitly compute in that case?
I don't know, should to say there are some technicalities that deal with relaxation in DB, and I really don't know something about anything about that. And there is for sure something precise about it, and for sure the unknowns because she got two partitions, but actually, one of the things that I would like to do is do some numerics on this stuff because it's, I don't know, somehow it misses something. You have all this nice structure and results, but you don't know how to compute things. Also because Gamma-convergence has this, I don't know, I'm starting.
No, it's okay. It's okay. You're still answering because I mean, you say that you may also have some result like that, but it's not constructive, it's by compactness, so you want to compute G in a sense if you want a complete numerical answer. But to compute G, my question was if you have any guess.
No, this actually, I've been asked this every time I do this talk more or less, and I actually don't know because it's not, I really don't know what to say. Also numerically, there is no, I mean, there is no result because I don't know how to compute this level, so actually, I don't know where to start.
Any other question? It's true that you put yourself already all questions, no? You kept saying that I'm asking myself, so questions are over. Thank you, Martino, for this. Thank you again. E tu ti sei fatto tutte le domande da solo.